Greetings. This is the review for the first midterm. It's in week 6 of classes. It's a little convoluted this year because the tests are split into two banks, some in the Pollock Testing Center and some when we can't get into the testing center to be done wherever you wish to do them. Anyway, so all tests this year will be closed book and closed notes. You're allowed, if you take the exam on the days you take the exam in the testing center, to bring a calculator and a pencil. They will supply you with scratch paper to write on, and your answers will be submitted on Canvas in the testing center. And so in week 6, 2 of the tests on the Monday and Wednesday are in Pollock. That means that they're open all day. You can take them anytime during the day that they're available. They're all 30-minute slots that are available for you. And because we can't get the test center on the Friday, it'll be online during class time, 8 till 8:30 on Friday, and again on Canvas, and you can choose to do that where you wish. If you want to go to the classroom to do it, that's fine, but if you want to do it at home, fine. You should do it alone, though, at home. The reason that we're moving the tests into the Pollock Center is because there was talk about widespread collusion last year, and so I want to be able to control that. There's a practice exam online on Canvas. We talked about either the first or the second periods. It has an exam script. It was actually the exam for last year, the first one, the Monday exam for the first midterm. And if you scroll down through the exam, if you take the exam, you can take it as many times as you want. You'll see there's also an equation sheet attached. And the equation sheet is actually just a screenshot of what I will go through later on today. And so the equation sheet that is available is what is below in this. In terms of the material covered, it's the first 3 and a bit weeks. We covered fluid properties in the first week. We covered fluid pressures at a point in the second week. We talked about integrating those fluid pressures on structures in the third week. And the first period of the fourth week was dealing with accelerating fluid. And so that is the scope of the material that these are taken from. The purpose of this review session is actually to clue you in a bit more granular detail on what we're talking about. And so the actual exam questions follow this format for Monday, Wednesday, and Friday. The 3 tests, you need to take all 3. So don't do as some students have done in the past. Contact me at the times of the second exam and say, oh, I didn't realize I had to take all 3. I just chose 1 out of the 3 to do. That won't quite work. So take all 3. The Monday test is on fluid pressures on structures and modes of failure. The second one on Wednesday includes ideal gas law, pressure at a point, and buoyancy. And the third one on the Friday is for a linearly accelerating fluid. So that at least gives you somewhere to look in your notes. To follow exactly what I will talk about here. Maybe look at prior exams. Certainly if you look at prior exams, you can see that the review sessions hopefully cover everything you need for that exam. You'll be able to see that, and you can check that for yourself because you have the corresponding review sessions and you have the solutions to the exams. So anyway, I won't talk broadly about the whole class. I won't review the whole class, but I will review all the things that you should need on those 3 occasions for the individual midterms. So for fluid properties, you need to understand the ideal gas law. You need to know that pressure is equal to the product of density, gas constant for whatever the gas is, and the temperature. The pressures and temperatures have to be absolute pressures and absolute temperatures, and so you need to be careful to do that. This gas constant is a specific number for a specific gas. And if you need that, you'd be given that. Density, of course, is the ratio of mass to volume, kilograms per meter cubed. And so you know that if you have this, if you have a structure, for instance, which is a closed system, then the mass should remain the same. The volume might change, but the mass would remain the same. And so you can use that to, say, calculate changes in density. If you have a flexible membrane like a balloon, you could imagine that the pressures acting on the outside and the inside are similar. They can only be changed by the stretching of the membrane, which is typically trivial. And so that should allow you to be able to evaluate what the equilibrium pressures should be on the inside versus the outside. And we talked briefly about balloons, how the density inside a balloon has to be different for buoyancy from that outside. And if that's the case, you can restate the ideal gas law to say how you get that condition. So to decrease density, you could either decrease the pressure, which for a balloon doesn't work because a balloon would collapse because the membrane's flexible. Or you could increase the gas constant by using a lighter gas, or you could increase the temperature by heating it up. So those are all the ways that you could make a balloon rise. So that's what you should need in terms of fluid properties. No viscosity, you don't need that this year on the thing, so you can count on that. Fluid pressures we defined in the second week. We developed some expressions for how pressure changes with elevation, which is that as you go up or down in a liquid, the pressure changes according to the unit weight of the fluid. For an incompressible fluid like a liquid, the density and therefore unit weight is constant. And for gas, the density is a function of the ideal gas law and changes with pressure. And we have to integrate that into our understanding of it. So when we try and integrate pressures in the column, if we're in a gas, because the gas is compressible and is most dense at sea level and is least dense higher up, we have this nonlinear distribution. We happen to derive an equation for it. And if you're in an incompressible fluid, a liquid, it varies with a constant value of this specific weight. And therefore, the rate of change of pressure with depth is a linear one. The rate of change is constant, and it gives a linear pressure, not gradient, it gives a linear pressure trace with depth. And we can get that linear pressure trace just by integrating the equations and working from the pressure at the surface to get the pressure at any point we want is just equal to the depth of that point multiplied by the unit weight of the fluid. Our sign convention is typically to have z positive upwards. It is in these equations. That's why the reason that the negative sign is here. But that doesn't, if you measure this down from the surface and keep it positive, then that would give you the right number for the pressure variation with depth. We don't have manometry in this test, but you know the manometry rules. If you go up in a fluid, you subtract pressures. If you go down in a fluid, you add them. If you go up or down in a gas, the gas density is usually low compared to liquids in the measuring system, and so it's inconsequential. If you have a vapor in contact with its original liquid, then it's acting at the vapor pressure. And you define vapor pressure in terms of absolute pressures. So vapor pressure would be close to zero absolute or minus 100 kPa gauge pressure for something like mercury, which is a very low vapor pressure. But as I said, you actually don't need that. So that might ease your pain in all of this. There will be something on pressures and forces acting on structures. And so we've talked about the three things that we want to do there. They're actually listed on this slide. We'd like to be able to calculate what the force is that's acting on the structure, the resultant force. It's always given by the unit weight of the fluid, the depth of the centroid, and the area on which that force acts. These two components here are just the average pressures. And multiplying the average pressure by the area gives the resultant force. And the centroid is always the balance point, if you like, of the plate. This is for a planar structure, and it's the depth vertically from the surface down to that centroid. So we can always get the resultant force acting on that. Resultant always acts perpendicular to that plate, but it acts not at the centroid, but at the center of pressure. And the center of pressure is given by this slope distance down from the surface of the fluid. The distance is we've called y sub r, and the location of that point is at some slope distance y sub r from the surface. And y sub r represents the distance to the centroid, the slope distance to the centroid from the surface, but also some other small component below that. And that small component is given by a standard result. These are just the second moments of area around the surface, and they're standard results. You've seen them before. They're things like, for a square plate, I think, where B is vertically downwards. This is A and this is B, and this is the surface here. Then these components are something like xc is equal to 1/12 a b cubed. So the units are in, to the power 4. It has to be to the power 4 of length, because this is length, this is area, so this is cubed. So something to the power 4 will give you a length, and adding a length to a length gives you consistency in your units. So you can always get it from that. You can also use standard results for these distributions. You know, for instance, that if you go down depth from the surface, then the pressure changes linearly with depth, and so the magnitude of the depth at which the force acts as the resultant is equal to 2/3 of the depth below the surface and 1/3 up from the base. And so this complete depth, of course, is the height of the pressure distribution acting vertically within a fluid. And of course the fluid is here, that this is the fluid pressure 0. So you can always use that to get that. So we know how to get the magnitude from this simple expression. We know how to get the point of action, y sub r, slope distance down in the plane of the surface that you're evaluating the pressure. And you can also take moments around points to be able to do that. If you want to determine the point of action of the force, you can take moments around any arbitrary point for the force multiplied by its lever arm. But if you're dealing with in failure modes, the hinge that you take, or the rotation point that you take, has to be exactly the failure mode that's occurring. So you have to be aware of that. So what you can do, we've done examples like this in class, where you have a distribution of pressures acting on a plate. That plate pivots. And so what you could do in this particular case is you could determine the magnitude of the force due to the rectangular distribution. Because it's a rectangular distribution, it has to act at mid-height of this distribution, and that would be the resultant for this force of this area. And then the resultant for the triangular area would act at 1/3 of the height of this, 2/3 down from the top of it, 1/3 up from the bottom. And the magnitude of this force would be the area under the triangle. If you wanted to calculate exactly where the resultant was working, you could choose to take moments around any position that you want. And here we're going to do this. And you could write this equilibrium equation in terms of the moments. So the force due to the prismatic distribution multiplied by its lever arm is this moment going clockwise. The force due to the triangular distribution times the lever arm is this force, again going clockwise. And that has to be countered actually by a force in the other direction. It doesn't really matter here, multiplied by some lever arm, which we don't know. Fr, we know, has to be equal to the sum of these other two. And so we certainly know what this is. And the only unknown in this expression is this equation here. So we should be able to solve for that. So you can solve for this lever arm. So that would give you an ability to be able to calculate exactly where the point of action is, but it's actually exactly the same as using this equation. My reason for introducing this is that often you want to be able to do things to calculate how pressure distributions acting on structures would affect that structure. And so if you have a pressure distribution acting on some kind of gate, then if you want to calculate exactly what this resultant is due to the pressure distribution, F sub r, and if you know that this dam to fail is going to rotate around this toe, then what you'd want to do is be able to use the centroid of mass of this, the centroid or center of mass of this dam, to look at the weight of this dam and acting against it. And we've done some questions in class related to that. And so you can also take moments about this to be able to balance those. So that's a useful thing to be able to remember and to understand. Buoyancy. Buoyancy we explained in class, is always given by the fact that if you go down in a fluid, the pressures at depth are larger than shallower up. And that increase in pressure is exactly balanced by the unit weight of the fluid in the mass that's above it. And that has to be true because this is an equilibrium, because F equals ma is being balanced. If you remove this weight of fluid, then all of a sudden this force acting upwards on this imaginary structure that you've taken the fluid out of has to be a bigger force than is acting downwards. And so the net buoyant force that comes from that is always given by the unit weight of the fluid that's surrounding this, that you've removed, and multiplied by its volume. So it's always the unit weight of the fluid that's removed. And so in this case, it would be the fluid that is surrounding this little bucket that we have in the subsurface. And that will always act through the center of buoyancy, which would be the centroid of this component. And it's always going to act upwards. It will always act against gravity, in the opposite direction from gravity. And so you can do a calculation. If there's some weight of this structure that is acting downwards and the buoyant force is acting upwards, then you can do the balance between those. I guess if you were true to the particular sign convention here, this would be weight acting downwards, which is minus, plus buoyant force acting upwards equals 0. And just from the sign convention, force upwards, weight downwards of this structure, and that would give you the result. Yeah. Finally, the final component is to use accelerating fluids. And we can think of the expressions that we develop for accelerating fluids. If it's a closed system where it's moving horizontally at some acceleration ay, accelerations are always positive in the direction of the positive coordinate system, then it will try and rearrange its free surface. But if it's a closed system, it won't be able to do that. And what it will do is it will just change the pressure distribution as you go across the base. And the pressure distribution that you get would be proportional to whichever direction you're going in. So if you're going across the bottom of this structure here, which is closed, the change in pressure as you go horizontally would be equal to the density times the acceleration. The acceleration is always a constant value, and so the rate of change of pressure would be just a linear distribution as you go across here, kind of shown here. If you were only accelerating horizontally and not accelerating upwards, then in that case this value of z would be 0, and so the pressure change with depth would just be the same as in a swimming pool, as if it was open. So that applies for a closed system. If you apply it to an open system, say a tank in which the top is open, then what will happen is as you move to the right by accelerating in the y direction, you'll rearrange the surface and it will become inclined, and the inclination of this surface is given by this. The slope is just the vertical and the horizontal, dz dy, and given by the horizontal acceleration in the y direction, again constant. And if there is an acceleration in the vertical direction, the addition of that onto gravity. Az is positive because it's is positive upwards, as opposed to gravity, which we know acts downwards. So that you have to be mindful of that. And so in this particular case, if you have no horizontal direction acceleration, but if you have an acceleration in y, which is not equal to 0, then you can calculate the slope from using this, where this term would be 0, and gravity is acting. And if you were, for instance, putting this in an elevator and doing the opposite, putting an acceleration in it, which is, well, I meant that this is equal to 0 in this particular case, equal to 0. So if this is equal to 0 and this is not equal to 0, you'll get a slope on this, as we defined. And in the converse case, when the acceleration is not equal to 0, but if the acceleration in y is equal to 0, then this would be 0 and this would be non-zero here. And so you can then calculate the slope of this. The negative sign is because the sign convention, this would be a negative gradient in that quadrant. This would be a positive gradient in this sign convention. And this is for a positive acceleration to the right. And this is for a positive vertical acceleration upwards. And so you can use that as well. So hopefully those expressions work for you. If you don't believe me that I'm trying to help you out by giving you the expressions you actually need to do well in the test, then look at the previous tests and compare the review sessions with them to see if you can find an expression you needed in the test which wasn't brought up in the review. I don't guarantee that it's in there, but I'm pretty sure it is, to the best of my knowledge. Okay, week 6. Good luck on the test. Thanks.